Hello everyone, my name is Andrew Kim and welcome to my last video for AP Physics C1 review session. So in this video, I'll be going through the last unit, which is about torque and rotational force. So let's get started. So now we have torque. First of all, as always, let's start with the definition of torque, or my definition of torque. So I would like to define torque as the rotational force, or the force that rotates the object. Now, what's interesting is in the previous units, we have only talked about forces that's applied to an object that does not have volume. We only considered point mass, a point that has a mass. Thus, if we apply force onto this object, obviously the object won't rotate because, think about it. If there isn't a volume, if it's simply a point, how can that point rotate? In order to rotate, the object should have a volume because rotating means the orientation of the object is changing. But if it's a point, then there's nothing such as orientation for a singular point, right? However, now in this last unit, since it's the last unit and probably one of the hardest units, we're actually going to take account of the volume of the object. And now that we have a volume, if we apply force onto the object is not simply going to slide in one direction, but it's going to rotate, it's going to turn. Now, since I mentioned how this unit might be one of the hardest units, the thing is, yes, torque is the hardest unit. It might be one of the hardest units, but still, since the topic itself is too hard, the questions aren't going to be so deep about it. It's not going to go deep into the concepts, but it's just simply going to ask the basic fundamental understandings about the rotational force. So you don't have to worry a lot. Plus, I checked the AP guideline and saw that in AP Physics 1 test, torque only takes 4 to 6%, I believe. It took the least amount of portion in the AP test. So you won't really have to worry about this, but for perfection, of course, you would have to study for this unit as well. So going back to our topic, now we're talking about forces that are applied to objects with volume. Thus, the object can actually rotate. And that's why I would like to define torque as the rotational force, or the force that rotates the object. And of course, in equation, we can express torque, which is tau, or this Greek alphabet that looks like T, equals to F times X. Now, why is tau or torque equals to F times X? Well, if we think about this, F is the force. Obviously, rotational force, or force that rotates the object, would be dependent on the force itself. If we're pushing this object with higher force, of course this object would rotate faster. If we're pushing this object with less force, then of course the rotational force, which is the force that rotates the object, would also be less. That is why for tau, in order to calculate the torque, you would have to take account of force. However, force is not the only factor that determines the value of torque. Even if the force is extremely strong, if you're not hitting the right position, for example, look at my camera, not the screen. If you have, for example, what I'm holding is an AC remote control. Even if the force of pushing this remote control is really big, if you're not pushing on the proper position, for example, if you're pushing on the exact middle of this AC remote control, you can see how the remote control is not rotating. Why? Because you're literally pushing toward the axis. If you're pushing at the axis, of course, the remote control is not going to rotate. However, if you push somewhere far away from the axis, you can see how even with less force, the remote control would rotate better. So now what we can know is that torque is a product of force and the distance from the axis. We can also think it this way. In English Premier League, or in the English Football League, they have there's a football player named Haaland. Now this guy is 4 meters tall. So that would be about 13 feet. He's really tall. So his legs are also extremely long. So even with the same force, if he kicks the ball, even with the same force, his x, or the distance from his feet to the axis of the rotation of his feet, is extremely long. His leg is extremely long, that even with the same power, still he can kick the ball much stronger because he's rotating his legs so much fast. So that's one thing. That's why he's doing extremely well in the league. But anyways, that's why tau, or torque, is equal to F times x. Now, let's talk about equilibrium. Before, when we think of equilibrium, it's the state when the net force is zero. It's the state when an object would just lie still on a surface or hang still on a rope or whatever. It's a state where the net force is zero, thus there's no acceleration on the object. The object will either stay still or move on a constant velocity without change in velocity. However, now we have to not just consider the net force, but now we have to consider net torque as well. Because even if the object is staying still, if it's rotating on its position, then we can't say that it's on equilibrium. It's literally rotating. So in order to say now, if you're considering the volume of the object, then when you say that, if you say the object is at equilibrium, it means that the object is in both equilibrium in terms of torque and equilibrium in terms of force and horizontal and vertical force. So now, let's think about a sample question. So let's say you have a seesaw. On one side, there's a kid who is 50 kilograms sitting, and on the other side, there's a kid who's 25 kg sitting. However, the 25 kg kid is sitting only 10 meters away from the axis of the seesaw, whereas the other kid, the 50 kg, the fat kid, is sitting 20 meters away from the axis of the seesaw. Now, first of all, let's think about force equilibrium. Let's think about vertical and horizontal force equilibrium. First of all, what are the forces present in this situation? Obviously, you will have gravitational force caused by the two kids. So for the 25 kg kid, the gravitational force made would be 250 newtons. And for the 50 kg kid, the gravitational force will be 500 newtons. Now, in order, if you want a situation where the seesaw is at equilibrium, of course, the vertical force should be canceled out and there should be zero net force, meaning that there should be a force heading towards upward, which is the opposite direction of gravitational force. And that force, that opposite force, that upward force, in this situation would be the normal force caused by this axis, this triangular axis in the middle. And that should be equal to 250 plus 500 in order to cancel out the two and maintain equilibrium. Thus, the normal force will be 750 newtons. Now, we found out that a situation where this seesaw could maintain equilibrium in terms of vertical force. Now let's think about horizontal force. Is there any horizontal force present in this picture? Well, there isn't, because every force is either gravitational force or normal force, and they all point either strictly downward or strictly upward, meaning that they would be only vertical. There won't be any horizontal force present. Now, we calculated for the force for equilibrium, for vertical and horizontal force. Now, let's think about torque. When we think about torque, since we consider this middle triangle as the axis, we have two torques present. First torque is caused by this 25 kg kid. Now, what would be the force? What would be the torque caused by this kid? Well, again, torque is equals to F times X, meaning that the torque will be 250 newtons times the distance between this kid and the axis, which is 10 meters. So it would be 2,500 newtons. Now, if the second source of torque would be this 50 kg kid. This 50 kg kid would also cause the seesaw to rotate, but in a different direction as the 25 kg kid. And the magnitude of the force the force of the torque caused by this 50 kg kid will be again tau equals to F times X, which is equal to 500 newtons times 20 meters, which is equal to 10,000 newtons. Now you can see how in terms of force, in terms of horizontal and vertical force, this seesaw had an equilibrium. However, in terms of torque, the seesaw did not have an equilibrium because the torque caused by one kid, one source, was only 2,500 newtons, while the torque caused by the other kid was 10,000 newtons. It's 4 times greater. Thus, the torque that torque on clockwise direction is greater than the torque towards counterclockwise direction, meaning that this seesaw would rotate in a clockwise direction. So as a result, of course, this seesaw is not in equilibrium because the torque is not in equilibrium. So now when we get to these type of questions, when a question says that a certain object is at equilibrium, now we have to also consider the equilibrium in terms of torque, not only equilibrium in terms of vertical and horizontal force. Now let's move on. What's interesting is we can draw a parallel between just linear kinematics and rotational kinematics. First of all, X in linear kinematics meant displacement, or the position that the object moved. Now, in rotational kinematics, we use theta, which is the angle that a certain object moved. Think about it. X, or displacement in linear kinematics, is how much the object moved linearly, how much it went forward or backwards. Theta here shows how much the object moved, not in terms of like literal distance, but in terms of angle. Because in rotational kinematics, what it all matters is not the length, but the angle that a certain object travels. Thus, we use theta. Now, the relationship between theta and x is that x is equal to r times theta. Now, r is the radius. Now, you might ask, why is x equal to r times theta? And I would like to explain it in this way. Of course, if you guys know the concept of radians, then it's going to be great. Everything's going to make so much sense. But not everyone is familiar with math, so I'd like to explain in a slightly different way. So x is the linear length, linear displacement, or literally how much this guy moved. Now, in this situation, in this pizza situation over here, in this rotational situation, the literal distance, not the angle, but the literal distance moved by this object would be x, and that would be the length of this arrow, this curved arrow. Now, what we're saying is that x is equal to r theta. This is because, think it this way, if theta is greater, it means the object rotated more, meaning that, of course, the linear distance that the object moved would also be greater because you simply moved more angle. That's why x is proportional to theta. Now, x, or displacement, is also proportional to r, or radius, because even if you move the same angle, if you moved in the same angle with greater radius, let's look at this image. Even if you move same amount of angle, even if you move theta, if you move in a greater radius, then of course, the literal distance, the literal curved distance that the object moves would also be greater because the radius is greater. Thus, what this tells us is that x, the kinematic distance the object moved, is also proportional to r, or the radius. Thus, we can make the formula x equals to r times theta, where x means the literal kinematic linear distance the object traveled, while theta is rotational or angular distance, or how much degrees the object rotated. And the relationship between the two is, again, x is equal to r, the radius, times theta. Now, what's interesting is we can use this relationship, we can apply this relationship to different variables as well. Omega, angular velocity, and v, linear velocity, also has the same relationship. linear velocity equals to radius times angular velocity. This is also very obvious if you think about it. Angular velocity is the ability of the object to change its angle, which means, of course, if you have greater omega, it means that you can rotate more in a given time. Thus, if you rotate more, then the linear distance that you moved would also be greater. That's why V and omega are proportional. And with the same logic as above, of course, V and R would be proportional. So that's why you can make the formula V is equal to R omega. And again, with the same logic, you can make the next equation, which is A, the linear acceleration, is equal to R times alpha, where alpha means the angular acceleration. So always think it this way. Linear equals to radius times rotational. Linear distance equals to radius times rotational distance. When you say rotational distance, it means literally angle, because how much distance you rotated is literally the angle. So linear distance, x, equals to radius times rotational distance, where rotational distance also means angle, and angle can be expressed by theta. Same, linear velocity equals to radius times rotational velocity, where rotational velocity can be expressed as omega. Linear acceleration, a, is equal to radius times rotational acceleration, where rotational acceleration means alpha. So I want you guys to understand this relationship. If you want to switch one term in linear concept to angular concept, then what you simply have to do is you have to simply multiply r, or radius, to the angular concept. Then you can get the linear concept or linear variable. So once again, theta is the angle that you rotated. Omega is how much angle you can rotate in a given time. And alpha is the change in the rate of change in your omega. How fast can your omega change? How can your angular velocity can change? How faster and faster can you rotate over time? Now, that being said, I hope you guys remember this formula F equals to ma in linear dynamics or kinematics. Now, F is equal to force, m is equal to mass, and a is equal to acceleration. A, or acceleration, in rotational angular world is alpha. F, the force in rotational or angular world, is torque, tau. Then what is m? Well, m in rotational or angular world is called I, or we also call it as the rotational inertia. Rotational inertia. You can see this sign. Rotational inertia and mass are similar. They are similar concepts. Only difference is that mass applies for linear kinematics, and rotational inertia is what you use in angular kinematics. Now then, what specifically is inertia? Well, since rotational inertia is literally the same concept as mass, but you're just using it for angular world, you first have to fully understand what mass means in linear world to figure out what rotational inertia means in angular world. Well, mass in linear world means, wait, what does it mean? When I ask this question, a lot of people respond by saying mass basically tells how heavy a certain object is. This is completely wrong. How heavy a certain object is not mass, but weight. And weight is literally gravitational force caused by mass times gravity, or gravitational acceleration. Mass itself means something completely different. Mass itself tells the resistance of the object in terms of changing its velocity. Think about it this way. Heavier person is harder to change its velocity because they're heavier. Even if you push the heavier person, it's going to be harder to change their velocity compared to someone who's really light. Mass is basically, it shows how its tendency towards not changing its velocity, towards maintaining its velocity. Mass is basically an indicator of how well a certain object can maintain its current state. That being said, rotational inertia means literally the same thing in angular world. It means how well a certain object can resist towards rotating. Meaning that if a certain object has high rotational inertia, it means that it's harder to rotate that object. Now, then when is rotational inertia higher? Well, think about it. Which object is harder to rotate? An object that is extremely tiny or an object that is very long and lengthy? Well, it would obviously be the object that is long and lengthy. Now, this might not be obvious, in fact, but let's think about it this way. You have two stakes. One stake is longer than the other, and you want to rotate both of them. Now, if you rotate the first object with force F, then basically the torque applied to this, then since torque is equal to F times X, if X is shorter, then you will need less torque in order to rotate this object. Whereas if you have longer X, if your stick is longer, more widespread, then you would need more torque to rotate this object. So what this basically tells is longer objects, more widespread objects are harder to rotate. Thus, what we can tell is that rotational inertia of more widespread object is greater than the rotational inertia of a more compact object. I mean, think it this way. So I talked about the football player, the extremely tall football player. Let's talk about him again. So there's a 4 meters long football player, and his legs are like 3 meters long, and he's sleeping. Whereas there's a little kid, he's 1 meters tall, and his legs are 50 centimeters long. Now think about it. If both of them are sleeping and you have your laptop under their feet and you want to get the laptop, so basically you have to lift their legs. You have to rotate their legs up in order to take your laptop. Now, whose leg is it going to be easier to lift up or rotate? Obviously, the baby's leg, because it's shorter. So what this tells is that more widespread objects have greater in rotational inertia. And that is why sphere has a greater rotational inertia than a disk, and a disk has a greater rotational inertia than a ring. I believe I said that wrong. It's the exact opposite. The ring has the greatest rotational inertia because ring is the most widespread. It's vacant in the middle, but it's all the mass is located at the outer part of the object. So it's more widespread. The mass is more widespread. So again, using this lifting leg analogy, you can see how if the mass is more widespread, it's going to be harder to rotate the object. That is why ring, which is more wide, whose mass is more widespread, would be harder to rotate. In contrast, if you think about sphere is the most compact, it's the most dense possible shape in the universe, because in terms of sphere, every point mass, every particle, every molecule that forms the sphere is going to be located on the least amount of distance possible from the center of the sphere. It's the most compact form. That is why the rotational inertia of the sphere would be less, and the disk would be in the middle of the two. Now, I'm done explaining. I have one more concept to explain, which is conservation of angular momentum. Now, just like linear momentum, the angular momentum also conserves if there's no outer force. Now, the formula for linear momentum was P equals to mv. Now, m in angular world is I, or rotational inertia, and v in angular world is omega, or angular velocity. Thus, angular momentum is equal to rotational inertia times omega, and that the product of the two should conserve, even if collisions happen. For example, you already have a disk that's rotating, and if you if you put another disk on top of the disk that's already rotating, then and the two disks starts rotating together, the initial angular momentum of this one singular disk and the final angular momentum of the two disks combined should be equal. So think about it this way. If you add another disk on top of the existing disk, then the rotational inertia, or M, would increase, right? So in order to maintain the same angular momentum, in order for the angular momentum to conserve, since I increases if you add another disk, omega, or the angular speed, should decrease, meaning that the disk would rotate slower. So that is the whole point of conservation of angular momentum. So if these concepts are not clear, then always try to find parallel between linear kinematics and just simply try to use the concepts from linear kinematics to solve questions in the angular kinematics. Now, so that was it for my explanation in the concept, but angular momentum and torque is a very tricky unit. Simply just explaining through the concepts might not solve your curiosities. So I'm going to explain how you can actually solve the question. One question type is a gigantic pulley, a huge pulley, a pulley that actually has volume and a pulley that actually rotates. Now let's think it this way. If you have two weights on each end of the pulley, then what would be the net force? First of all, you can see how one gravitational force is pulling 30 newtons towards down on the left side, and the other weight pulls 50 newtons down on the right side. Thus, the net force caused by the two gravitational force would be 20 newtons pulling towards downward on the right side, meaning that on this pulley over here, we have 20 newtons of force applying towards clockwise. Now then, what would be the torque that's applied onto this pulley? Well, again, torque is equal to F times X, and F is the force, which is 20 newtons in this situation, and X is the distance the force is applied from the axis of the rotation. And since the axis of the rotation is this green checkpoint, and where the force is applied on this pulley is on the top, on the tangent line, or on the circle of this pulley, the X, or the distance between the two, would literally be the radius of the pulley. Thus, the torque applied onto this pulley would be equal to 20 times R, 20R. Well, R might be given from the question. If that's the case, then you can simply plug in R and then solve the problem. Now, the second situation is when a ball is rolling down a hill. Now, what's important is that the question is going to ask the question in two different ways. First is when friction is not present, and second is when friction is present. Now, if there's no friction between the ball and the slide, then the ball is not going to rotate. I mean, think about it. Why does ball rotate in the first place? Well, that is because there's friction. So the ball wants to just slide down, but since there's friction, the velocity on the bottom part of the ball will be slower because there's friction applied to the bottom part of the ball, whereas on the top of the ball, there's no friction. So the top of the ball will have higher velocity than down of the ball, so the ball will going to rotate. That's why the ball rolls down. So if there's no friction, then that means the ball does not rotate. Thus, it's fine to just forget about rotational energy or whatever, and just do your normal thing as if this ball was a point mass. However, if there is frictional force involved, then things change. If friction is present, then as I explained, the ball will start rotating. Thus, the only types of energy that's present is not simply kinetic energy and potential energy caused by the gravity, but there will also be the third force, which is rotational energy. Now, then people might ask, how do we calculate the rotational energy? Again, if you're confused in angular kinematics, then try to find parallel between kinetic linear kinetics. And in linear kinetics, the kinetic energy was equal to 1/2 mv squared. Now, What is m in rotational world? It is I. What is v in rotational world? It's omega. Thus, we just induced the formula. The rotational energy is equal to 1/2 I omega squared. Thus, if the ball rolls all the way down down the ramp, then of course there won't be any more gravitational energy left because now you're on the ground. So the only energy present would be kinetic energy plus rotational energy. Now the kinetic energy would be equal to 1/2 mv squared, and the rotational energy is, again, as I wrote over here, it's going to be equal to 1/2 I omega squared. And that will be equal to the energy, the conservation of energy, the initial energy of the ball, which will be potential, gravitational potential energy, which is mgh. Now, it's kind of weird, right? Because in order to make this equation, I literally used the conservation of energy. However, we had the assumption that there's friction involved. And if there's friction, of course, the universe in this system as a whole, there's no change in energy because in a closed system, energy conserves. But if you only look at the ball, then the ball would lose its energy if there's friction present. It would lose its energy in a form of heat and probably sound when it rolls down the ramp if there is friction present. However, when the question says that there is friction present, it's simply saying that the friction is there just enough to make the ball roll. It's not significantly, it's not big enough to actually slow down the ball and actually reduce, actually take up the energy from the ball. It's only there, only a bit, only slightly to make the ball roll. So you can still use the conservation of energy. Now, what we have over here is 1/2 mv squared plus 1/2 I omega squared equals to mgh. Now, this equation looks painfully complicated because you have m, you have g, you have h, you have v, you have I, you have omega. You have 1, 2, 3, 4, 5, and 6 different variables in one equation. However, in fact, this is not true. First of all, g is an alphabet, but it's not a variable. It's a constant. It's always 9.8. M is indeed a variable. H is also indeed a variable. But V, is V a variable? Well, it is a variable. However, if you know, but okay, yeah, in fact, V is a variable. Let's go back to this later. V is a variable. Is I a variable? Well, I is a variable, but I is a rotational inertia. In AP Physics 1 level, the question will give you the value of I. It will give you the rotational inertia as a constant. So you can simply use the information from the problem for I. Now, omega, is omega a constant or a variable? Well, omega is a variable, but we know the formula V equals to R omega, meaning that omega could be calculated by V over R. Now, V is a variable, but R is the radius of the ball, meaning that it's a characteristic, it's a trait that the ball has, which means it's going to be given from the problem. Thus, omega is a variable, but it's literally a different form of variable of V, which is an already existing variable, meaning that omega is not a new variable that you have to calculate for. Thus, truly, the only variable that's present that you have to actually calculate for is M, H, and V. But what's more interesting is that, in fact, V can also be calculated using H because of this formula, the energy of conservation. Thus, really, it's only M and H that's going to be either given from the problem or calculate one of them using the other informations. So it's not going to be too hard. Always, it's good to substitute omega with V over R if you want to reduce the number of variables. So that was it. I both explained about the basic concepts of torque, and I also explained about some typical hard problem types that can appear in AP Physics 1 level torque. Again, these are hard problems. Pulleys rotating and a ball rotating down a ramp is hard enough to even come out in AP Physics C. Most likely in AP Physics 1 level, you're just going to encounter problems like you have a stick and you have force is applying in this and that direction, and the axis is at over this point, then what would be the net torque, or like what would be the angular acceleration caused by the net torque and stuff like that. It's not going to be really hard, so you don't have to worry about it. But I simply wanted to introduce some hard question types that might appear in AP Physics 1 just for perfection, because in order to be perfect, you have to know everything. So that was it. By the way, this was my last video of the series of 7 videos, one for each unit in AP Physics 1. If you watched all 7 of my videos, thank you so much, and you will be rewarded by getting 5 in AP exams, so you won't have to worry really. Anyways, you've studied hard, even apart from watching my videos. I know you studied hard for the unit tests, for the quizzes, and in the class as well, doing homework, doing web assignment and stuff like that. So trust in yourself. You'll do well in the AP exam. Good luck. Thank you for watching my video, and don't forget to have a great day. Bye.